The large language models nowadays are all based on transformers. And all the transformer models are models with an attention block. So attention and transformer basically mean the same thing. A disclaimer, some materials in the slides are borrowed from the Open NLP course from Stanford. And I'd assume that you have basic machine learning knowledge. This lecture is designed for people who know absolutely nothing about transformers. So you don't need to know transformers. Okay, I will first introduce what transformer models can do. Then I'll explain why is transformer better than RNN. I feel it's a necessary part to better understand why is transformer created in the first hand. And the most important part, of course, is the attention mechanism. I'll spend most of the time explaining how attention works. So when talking about the application of the transformer, you'll probably think about ChatGPT, right? How it works is that it takes an input text and gives you an output text. So any sequential input and output can be done by the transformer. Here I quickly introduce how the text data is processed in the transformers. When you work with image data, video data, or even robotic movements data, it can be a little similar, but like the text will be different, but eventually you'll all go through the process. For each sentence, we first break up the words into pieces, hello world, breaking into hello world exclamation mark, each word or token going to be an integer. And then we convert this integer to a one-hot vector. So one-hot means every place is 0, and on the 2088th digit is 1, and everything else is 0. So it's called a one-hot vector. And then you multiply a matrix to be a relatively complicated vector. This step is called embedding, and the above step is called tokenization. If you played around with my code I sent you in the email, all these can be done by the tokenizer. The main reason you do it is because all the models talk in numbers. They don't talk in hello world. So this is just one, like, everybody agrees upon way to transform a text into some numbers, right? And towards the end, when your model generates output, you do the opposite direction. You have this, and you convert that back to the token IDs, and then back to the text. All the transformers, again, go through the same process. Okay, so again, for text generation, remember that you're generating your output token by token. You don't just get the whole thing at this one time, right? So you generate token by token. That means when you're training, you cover the next token to be generated and see if it's the same as the label. So once you have this token, you plug it in and generate the next. So let's say I'm on the training process, training a model to translate from English to French. I have a cat, j'ai un chat. The training process goes like, I cover un and train un. And once I have un, I plug in un and generate chat, the last token, right? And this is, of course, a supervised training procedure. Every single token, you have a different token ID. But there are some very special cases, right? For example, chat is the same as chat, right? And it's the model's job to know, oh, this is in the output, this better be French. It means the cat, right? But it's the same token for the model. All right, let's move on. And other things that the transformers can do, you can also do text classification, right? A very classical example is classifying the sentiment of a Twitter post. That's one of the most popular hacking jobs for students when the transformers first came out. So the model reads a post on Twitter and tells you if it's positive, negative, or neutral. And you can classify images as cats or dogs with transformers if you want to. So later on, people realized that transformers might also work well on seemingly unsequential data and treat it like a sequential data. For example, in 2018, people started to use transformers on computer vision. So the task itself is to classify an image. Is it a building? Is it a view? Is it a person? Is it a cat or dog, right? The way it works is that it cuts the image into several pieces in identical shapes. So for example here, it's 9 pieces, and sequentially process each piece. So this is piece 1, 2, 3, 4, 5, 6, 7, 8, 9, and you treat that as a sentence, right? In other words, you treat each piece like a token, and you have a vision transformer called VIT to do that. At the current step, if you're looking at nowadays, transformers can process so many data types, namely audio, image, robust movements for both input and output. And that's why the theme of our project is multi-model, right? So multi-model spells like this. It doesn't mean you have many different models. It means that the transformer can process many kinds of data.
Modalities, this one, okay?
And we call it modality in a fancy machine learning way. So because the tasks are so diverse, there are various structures of the transformers designed for different tasks. This is how the transformer looks like when it first came out in 2017. It's the most conventional encoder-decoder transformer model. We have an encoder that reads in the input text. It understands the input, and the decoder that reads in the encoder information, as well as the already generated output here. So for example, in French, you take in this j'ai un, and you generate chat, right? And here's the English sentence, I have a cat. The graph on the left might be a little misleading in terms of how encoder sends data to the decoder. So on the right, remember that each layer of decoder takes in the same encoder output as the last layer. So rather than encoder 2 talks to decoder 2, it's like all the encoder processes the information, and towards the end, it gives a conclusion, which is a vector, and then this vector feeds into all the decoder layers. Therefore, you can have different numbers of layers in your encoder and in your decoder. In practice, most models have more layers in the decoder. So note here that the main reason you have an encoder-decoder structure is not because it's necessary, right? But because a lot of the machine learning in the past did this, such as recurrent neural network, autoencoder had this, and transformer at first just copied this. And then later on, people found out, oh, we actually don't need both encoder and decoder, right? The encoder or the decoder alone can handle all the tasks, and they can do pretty well, right? So having only one side, we reduce the model size and save computations, and that's what everybody wants. So actually, most transformer nowadays are either encoder only or decoder only. For example, the GPT family, and even ChatGPT till now, is a decoder only model. Right. And for encoder-only models, we generally use those for classification tasks, for example, BERT. But for education purpose today, I'll mainly introduce the encoder-decoder transformer only because it has everything. Reason transformers are a reduction on the structure of this model. So once you understand this, you understand all the models today. To start with the attention mechanism, I just think we should first understand why it is created in the first hand. Like, what is the purpose of this? Why is it so good? Before 2017, when you have a sequential data like a text, everyone uses a recurrent neural network, short as RNN. So shortly after Transformer came out, nobody uses RNN anymore, right? People just stopped publishing RNN papers after 2019. But again, it's still very beneficial in understanding this. Again, I'll use French and English because they're similar languages. I like to translate this French to this English. They both mean the same thing. The poor do not have any money. So most people don't speak French. I'll just briefly talk through. Like, les literally means the. Pauvre means people. Sont means are. Démuni means penniless. It's an adjective for do not have any money. In the middle is a structure of decoder, encoder, RNN. So what it does is that in the encoder, you take French token one by one. We start with les, right, for example. You first convert it to a vector x, going through the tokenization as we just discussed, same thing. And the RN itself is just like mainly two computations. The first is wx, the second is wh. They're called w's because the main part is a matrix multiplication. So you first multiply the first token with a matrix wx to get the empty circle here, which is a vector, and we call it hidden state. Then the second hidden state is the sum of the previous hidden state multiplies another matrix wh, and then the second token, which is Pauvre's tokenization, with wx. So it's the sum of this times this and this times this. And then you go forward, and so on. So note that RNN process each token sequentially. You process the first token, then the second token, then the third token. That's how it works. And eventually, at the last word, let's say you have already processed démuni, You put this last hidden state and become a cell vector with the same dimension as a hidden state. And when you're generating, use the cell vector and a beginning state to together decide the first hidden state. And this first hidden state becomes the first word of your output, which is the here. And then this the, together with the other hidden state, together with the cell state, generate a pour. Similar to how you do it in the encoder, you also generate decoder one by one. All right, so that leads to two problems of RNN. The first is that the encoder tends to forget about the early token. So think about how it does this. Right? So the first token is WX times something, and the second token is these two things plus together. Towards the end, this last token is look way more like the last token than the first token because you went through too many computations in the middle. That also leads to another problem during training, which is gradient explosion and gradient vanishing. So when you're doing gradient descent, you're going backwards, step by step, layer by layer. And let's say you have a very, very, very long text in your input, let's say 100 words. So this step goes back one word, and then this step, and then eventually at here, you went back 100 steps on the same set of parameters, WH and WX. So let's say this gradient is 0.99. And at here, this gradient might be 0.99 to the 100 powers. And that's very close to 0. And let's say this here is 1.2, and here is 1.2 to the 100s. It's going to explode or vanish. And it's very likely, and therefore, the length of the training set of RNNs has to be kept in a certain length. And there are later on different works that helps to solve this problem. Like, for example, LSTM. It has a forgetting mechanism that helps you forget some unnecessary steps in the middle, so it's better to do gradient descent. But what we're going to talk about today, attention mechanism, is a way better solution to these two problems. So what is our goal here? We need some mechanism that looks at all the tokens at each step. But of course, not all the tokens are equally important, right? So you also need to give more weights to more important tokens rather than to the later tokens. And that is the spirit of the attention mechanism. So finally, we're talking about attention mechanism. So this is the attention mechanism. Let's still use the same translation task. Notice that when you generate each word, you don't really need all the tokens from the input. For example, when you generate the pour, when you generate these two tokens, you only need les pauvres, right? Son diminués are not really relevant. The most relevant are les pauvres. So in order to avoid information bottleneck, we just need a mechanism that for each word we generate, we can get a different information that saves only the important information for the input. And how do we do that? We can let the cell vector be the weight distribution of hidden states, where the weight of each token is alpha. If you really need a word, you just give it a higher weight. So when you generate pour, you give the second hidden state a bigger alpha. And how do we make sure the weights sum to 1? We use softmax, which is a very common component in all neural networks. Basically, you take a vector, you go through softmax, and it gives you another vector that sums to 1 in the same proportion. And now let's see how the alphas are calculated in the first hand. Why or how can I get a higher weight for the important token? So before coming into the attention block, I want to make everybody be on the same page of each dimension of the input and output so that in the middle you don't get lost. You'd be like, oh, what is the shape of that? Oh, how can you do that? Okay, and here are how it goes. The input and output of each block in both encoder and a decoder is the same vector called hidden states. They're of the same shape as embedding, but it also has a text length and, of course, the batch size. Everybody knows what's batch size, right? So let's say I want to generate 10 sentences at the same time, and the batch size is 10, right? For encoder, the text length is the length of your inputs, how many tokens there are in the input. And for decoder, the text length is how many tokens you've already generated. Let's say the pour do not have any money, and I'm generating money, then the text length of decoder would be around 6 or 7, right? That's the number of tokens I've already generated. So it is a 3-dimensional vector. Now let's do an example, okay? When I generate the translation of this sentence from French to English, And as I said, I'm generating tokens one by one. I have already got the pour do, right? And I'm going to generate the fourth token. Assume the batch size is 1. I'm only generating this one sentence. And the embedding is 1024. So what's the shape of my hidden states? Anybody want to answer?
I don't know what the embedding is.
1024, I guess.
So embedding here means the dimension of your middle vectors. Let's say I have a really large model, then my embedding better be 5,000 something, because it saves more information. It's just the dimension of the middle vectors that you pass on to all the layers, right? I am generating the pour do, the next token after do. What is the hidden states shape for the encoder, let's say here, in this arrow?
4.
1,
Yes.
4,
4 and
1024,
1024.
right? And what is the shape of this vector?
It's the last layer.
That should be 1, 3, 1, 20, 24.
That's right, but not exactly, right?
Ah,
So
Last layer. No?
they're actually
yeah,
a start token
start token
and an end
end
token
token,
for
yes.
both input and output. These will be added automatically from a tokenizer. So the first one is actually 161024 because you added 2 tokens, and the output will be 1424 because you only added
But
start.
in general, it's correct based on what you saw, but
The vital things you need to know are query, key, and value. These 3 things plus together is basically the attention mechanism. So to begin with, I'll first let you know where these 3 names came from. They actually are borrowed from the database systems. Anybody writes SQL here? Okay, cool. So
in my bachelor's I wrote, in master's. Afterwards I
that's a bachelor class? No, that's a master class?
No, I'm BS class.
Okay, nice. Say you have a data set of employees and you want to get all employees whose birthday is in October, and you can write an SQL code to achieve that. And this SQL code at here is called your query. And since we're looking for birthday, then the birth date attribute here is called the key in this case. And all the attributes or the columns are the values that comes along with your key. Finally, this code will give you this, which is both key and value. In attention block, query, key, and value, or QKV, each represents a vector, and they're generated by multiplying the hidden states with a matrix. And this matrix is, of course, the parameter of the model, which is like learned and trained, right? Then we calculate the attention vector by multiplying Q, K, and V, or Q, K transpose and V. To make it super clear, now let's work out the dimensionality of each set. Remember that Q, K, V are 3 vectors. They have the same dimensionality, right? So Q is of shape. Can everybody remind me what it is? So it has batch size, right? Length,
and
and embedding. Perfect. And what's the shape of K? Same thing, right? So for batch size, we can ignore it for now because you're just repeating the computation for each batch you're generating. 10 sentences, we do it 10 times, same way. And now let's just see how it works. So Q times KT gives you what? LE times EL
Yeah.
gives you what?
And
LL, right? And that times V is what?
so LL into CL.
yes,
Again.
that's LDA name.
That's LE again,
Yeah.
right? Okay, cool, perfect. So we came from LE, which is the dimension of the hidden states, to LE, which is another shape of hidden state. Now let me introduce like what query, key, and value intuitively means. Like right now, they're just 3 random vectors that we created. So why do we do this? The weights are achieved by getting the dot product of query and key. So what purpose do we use dot product for, right? We usually use dot products to find the similarity between two vectors. The closer they are in the directions, the bigger your value will be. So the more similar they are on one token, right? Let's say in query you have age, the key you also have age in another scenario. Then the more important this token is in your key for your query. So the higher this weight will be, and therefore let's give this value more weights so that your final product on this digit will look more like your value. But for the unimportant tokens, they're going to look less like your value on that specific part or token. All right, that's the intuition. But for the model, it's just numbers and vectors. Right. So back to our example, right? Les pauvres sont démunis. So you'll have 4 keys. Key 1, key 2, key 3, and key 4. Remember what's the size of K, right? So it's L and E, right? So this is L1, L2, L3, and L4, and each one has an E. And when you do Q times KT, when you're generating the word after the, it should be poor, right? So this one should be big. And your result is L times L, which is 4 times 4, where you will have a very, very big second vector of embedding, and that's going to lead to a more important value. Okay. Again, it's all numbers in the black box, but this is an intuitive explanation of how it works.
About what it means.
Yeah, thanks. Okay, now let's come back to the
Self-attention.
classic graphs. This is the structure of the encoder-decoder transformer model. This is what ChatGPT looks like, right? We are at the very edge of understanding these 2 blocks and this block, which is called self-attention, updating the hidden states vector to understand your text itself. So now here's a writing diagram of self-attention process in the encoder. You have a text that you just want to have a better understanding of it. It's inside your encoder. So at first, you have break into these tokens, right? And here you have an L that is 8. And for the first token, you have a hidden state. You do the QKV stuff with all the other tokens you have. And then they're going to generate different weights. And here you get a new hidden state. Then you update this new hidden state to this one. And you do the same thing for the second word. And guess what? Because our GPUs can do parallel computing, you can do all these stuff at the same time. So understanding your own text is very paralleled and very fast. Okay, now here's another diagram for this process. Here, who can tell me what is the embedding here? Yeah, the embedding here is 3, right? This is the embedding, and the 4 is your text length. Okay, so you get your query with a WQ, you get your key with a WK, you get an intention filter, which is length times length, and then you times with the vector V, and you get a new hidden state. Easy peasy, right? And for this specific attention head, it's a little bit different because query and key and value come from different places. So previously, to understand your own text, it's called self-attention, where QKV just come from the same place. You're trying to learn a relationship between on and the other words, or cat with the other words. That's what you do for self-attention. And for cross-attention, you're trying to understand the current word that you're generating, the poor, versus les pauvres sont démunis, your relationship with your input. That's why query comes from your decoder, but key and value comes from your encoder, right? Because these two represent your input information, and query represents what you want in your output. Yeah, here, start, right? What should I generate for the first step? I ask my input, right? And of course, the query value comes from here as well, my current hidden state where there's nothing. The query value tells you that I am just starting, and key and value comes from these words in the input. I do the attention stuff, as I usually do. I generate a new hidden state for the decoder here because it's cross-attention, right? And I use this hidden state eventually leads to my first generated token, which is the. And I plug in this the, I get a new query telling you that I have one word now. What is the second word? I do the attention stuff and I generate the second token for, right? And I do this again, 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 and then it's done. Okay, so now you understand both cross-attention and the self-attention. And now let's just come back to this image. You'll see that everything is called multi-head something, right? So what is multi-head? It's a very, very simple stuff. It's just what you always do in convolutional neural network. Rather than extending the length of your vectors, you are piling up your vectors to different layers. So let's say I have a queue of batch size, length, and embedding, right? I'm saying like, oh, this model is too small. I want to have a larger model by increasing its number of parameters. So can I just have a larger E? Actually, the better way to do that, rather than making this E larger, is that I have different channels of E. Instead of making it 10 times bigger, I make this C10, and people find that it has a better performance. So that's what multi-head means. It just literally means that piling the vector like a couple times, but of course, the parameters are different. It's just a smarter way, a better way to increase your number of parameters. Okay, now let's move on to the last alteration on the attention block, masked attention. Right? So it only exists in models for text generation. When we're training the model, we're going to provide, of course, both the input and the output, right? Because otherwise, how can you train? Because it's the labels. So the problem is when we are generating poor, we are still feeding the whole sentence into the model. And if the model sees all the answers, it just learns to copy the answers and it learns nothing. So to make sure that the model does not see the answers, what we're going to do is that we're going to add a negative infinity to the tokens that we do not want it to see. So masked basically means I have an additional adding step that I'm just going to intentionally cover the tokens that are yet common. And that is especially for the generative training step to not let you see the answer. And lastly, the other parts of the model is just like what you'll always see in all the other machine learning models. They're not new. You'll see a softmax layer, you'll see a linear layer that transform your last hidden states to another dimension that can better transform to the tokenizer. And here you have an add and normalization and feed forward. This thing, so here is used in something called ResNet. You can look it up. It's developed by Google in, I think, 2018 or 2014, something like that. What it does is that it adds a skip mechanism. So here, instead of just only going to feed forward, you can skip this and add to something after the feed forward. The way to do that is that once you have so many layers, you have gradient explosion and gradient vanishing, as we talked about earlier. And this is a way to help your model still function very well. Finally, we have one last stuff. Positional encoding. This is not very important. It's been using by transformer developers for very, very long, so many years. But literally in June this year, a paper just came out saying that positional embedding is useless. But in case that your models might have this, I'll just let you know what it is, right? I have two sentences. AJ's dog is a cutie. AJ looks like a dog. Actually, this is a poor example, but think about another example. I cook good food, and he is a good cook, right? So cook appears twice here, but the two cooks mean different stuff. You can have very different meanings with the same word. And the different meanings really come from the fact that when a word appears at different places in a sentence, it can have different roles. So in order to reflect on that, we add another additional factor that only represents its position in the sentence. with its original embedding and get a new vector to slightly alter it so that this word does not only represent itself but also represent its position. The way that you generate this embedding position is from something related to sine and cosine. But again, as I mentioned, this is actually the end of May, it's proven to be useless. And so when you're implementing, you don't need to care about this part. And yeah, that's it. That's it for the talk today. Thank you so much.